In the early months of 2020, the world changed forever. Streets that once echoed with sounds of busy lives fell silent. Hospitals overflowed, doctors worked around the clock, and scientists raced against time to find answers. The COVID 19 pandemic was not just a health crisis, it was a global test of technology, resilience, and humanity. As nations struggle to contain the virus, one of the biggest challenges emerged in the field of medical field the rapid detection of COVID-19 infections. Traditional testing methods like the RT-PCR were accurate but time-consuming and often inaccessible in remote regions. Medical professionals needed something faster, something that could assist them in identifying infected patients early, especially when every second could save a life. That's when technology and medicine began to merge more closely than ever before. Researchers realized that chest X-ray images could hold critical visual clues about COVID-19 infections. The human eye, however, could only go so far. That's where artificial intelligence AI stepped in, not as a replacement for doctors, but as a powerful assistant. This project was born from that realization, a step towards building an AI-powered system capable of classifying chest X-ray images to detect signs of COVID-19. The idea was simple but ambitious. Train a deep learning model to distinguish between normal COVID-19, viral pneumonia, and lung opacity images based on subtle patterns that even experts might overlook. The journey began with data. Thousands of chest X-ray images, carefully collected, cleaned and organized. Each image told a different story. Some showed clear lungs, while others revealed cloudy patches, shadows, and patterns of infection. These patterns became the foundation of the project's learning process. The convolutional neural network (CNNs), the same technology that powers the facial recognition and self-driving cars. The model learned to analyze the complex features within X-ray scans through repetitive training, validation, and optimization. It started recognizing the difference between healthy and infected lungs with remarkable accuracy. But building the model wasn't just about numbers and accuracy metrics, it's about impact. Imagine a remote clinic in a developing area, limited resources, no access to advanced testing, yet equipped with a basic X ray machine and an AI tool that could instantly flag potential COVID 19 cases. This is where the project finds its true meaning, bridging the gap between technology and real world healthcare. Beyond the algorithms and architecture, this system symbolizes the power of innovation during crisis. It reflects how data science, when guided by empathy and purpose, can contribute to saving lives. The project is not just a technical demonstration, it's a glimpse into the future, a world where AI and healthcare work hand in hand to fight unseen threats. From pixels to prediction, from datasets to decisions, this project captures the essence of what AI stands for augmenting human intelligence, not replacing it. And while the pandemic may one day fade into history, the lessons and innovation it inspired, like this one, will continue to shape medicine for tomorrow. If you want to know more about EfficientNet, check out this video by Code with Arohi, Rethinking Model Scaling for Convolutional Neural Nets. Open app.py and write the following code. Step 1. Imports and Setup. Import OS for file and directory operations, NumPy for mathematical operations and array handling, TensorFlow for deep learning model training, sklearn.metrics gives tool for evaluation, accuracy, confusion metrics, etc. Matplotlib.pyplot for plotting graphs, iter tools helps in iterating over confusion metrics values, warnings.filter warnings, ignore, hides unnecessary warnings during execution. Step 2. Constant configuration. This defines fixed parameters for your model. Image size. Every image will be resized to 224 into 224 pixels. Batch size. How many images are processed together in one step. Data dir. Folder path where all your images classes are stored. Learning rate. How fast the model learns. Too high will result in unstable or too low will result in slow learning. EPOS, total rounds of training, and seed to ensure reproducibility of results. Load and prepare data. Train ds equal to tf dot carries utility image dataset from directory and validation dataset tf carries dot utility image dataset from the directory. Then we will load images directly from the image folder. TensorFlow automatically labels each subfolder as a class. Validation split 0.2 20% of your data goes to validation and 80% to training. Subset defines whether the dataset is for training or validation. Image size equal to image size, all resized to 224 into 224. Batch size equal to batch size, how many images per batch. Class names equal to np.array, train ds.classnames, num classes equal to length class names, print detected num classes class names. This extracts and prints the names of classes COVID-19, normal, etc. Step 4, I/O optimization. Autotune equal to tf.data dot autotune. Train ds equal to train ds dot prefetch. Buffer size equal to autotune. Validation ds equal to validation ds dot prefetch. Buffer size equal to autotune. Prefetch speeds up training by loading data while GPU trains. It ensures maximum hardware uses efficiency. Step 5 is data augmentation. Data augmentation equal to tf.curves.sequential, artificially increasing dataset variety by random transformations helps prevent overfitting. Random flip refers to the flipping of images in both directions. Random rotation 0.5 rotates the image randomly, and random zoom zero point 0.3 zooms in and out. Step 5 is building the model. Step 6 is building the model. Base model equal to tf.curves.applications efficient net v2b0 base model dot trainable equal to false. Uses efficient net v2b0 a pre-trained CNN for ImageNet transfer learning. We freeze it so it internal weights don't change. It acts as a feature extractor. Builds the custom head of the model. Input refers to defining the input layer size. Data augmentation applies random transformation. Preprocess input preprocesses image forms format to efficient net. Global average polling 2D reduces the large feature map into a single vector. Dropout 0.3 prevents overfitting, and dense refers to the final output layer with softmax activation, multi-class classification. Compile and summarize. Model.compile optimizer equal to tf.curse optimizers Adam learning rate equal to learning rate loss equal to sparse categorical crossed C metrics equal to accuracy model.summary. This defines how model learns. Optimizer Adam adaptive learning. Loss refers to the sparse categorical cross trony for integer level multiclass, and metric refers to the accuracy. Model.summary prints the architecture details. Training the model. Model checkpoint saves the best model based on validation accuracy. Early stopping stops training if validation stops improving. Starts the training starts training the model when training and validation is reached. Then we come to evaluation. Y true, Y predict for images labels in validation dataset. Loops the validation data to get true and predicted labels, and then it calculates the precision, recall, F1 score, and confusion matrix. Confusion matrix plot dev plot confusion matrix CM classes plot confusion matrix CM dot class names displays a visual matrix showing how many predictions were correct versus misclassified. Then final accuracy ACC equal to NP dot mean Y true equal to Y predict print final validation accuracy calculates the final overall accuracy by comparing predicted and true labels. Open interface.py and write the following code. Step 1 Imports. Import OS. OS used to access files and directories on your system. NumPy handles numerical arrays essential for image and tensor operations. CV2 Open CV2 library for image reading, resizing, and color conversions. TensorFlow deep learning framework used to load and run your trained model. Warnings to suppress unnecessary warning messages. Tinker built in Python library to create the graphical user interface. TK main window label to display text and images. Button for clickable buttons. Field dialog to set an image for your computer. Message box to show error or info in pop-ups. PIL or pillow used for opening and displaying images inside the GUI. Warnings.filter warnings ignored disables annoying warning logos. Step 2 is constant. Model path refers to the best COVID-19 model.h5 and data dir, the data folder. The model path is the location of your saved trained TensorFlow model.h5 format, and data dir the path to your folder where the training data was stored. Each subfolder refers to the one class. COVID-19, normal, viral pneumonia, Step 3 is load model and class names. Model equal to tf.curs model.load model path class names. The loads the trained model into memory using tf.curs.model.load model uses os.list dir data dir to recall all subfolder names, each represent a class, sorts them alphabetically to maintain consistency, prints the list of class names for verification. Image preprocessing. cv2.imread image path reads the selected image. If image is none, it means validation path or corrupt file raises an error. cv2.cvtcolor image cv2.color bgr to RGB converts the color from CV's default BGR to RGB. TensorFlow expects RGB. cv2.resize image 224, resizes the same input size your model was trained on. tf.cursor.applications.efficientNet v2.preprocess image applies standard normalization scaling for efficientNet v2. np.expand dimensions image x is equal to 0 adds a new dimension at start. Shape becomes 1, 224, 224, 3. Batch of one image. Outputs a single preprocessed image ready for prediction. Prediction function calls prediction image to prepare the image, preprocess image to prepare the image, model.predict image. Model outputs a probability vector for each class. np.argmax predict 0, find the class index with the highest probability, confidence equal to predict 0, class ID multiplied by 100, convert stop probability to percentage, returns class names and confidence pair. If any error occurs, it shows a pop-up message via messagebox.showError. Browse image function opens a file selection dialog so that the user can pick an image file. If a image is selected, it is opened using PIL. Image is resized to fit inside the GUI window, converts the pillow image to Tinker compatible format, image tk.photo image, updates image label to display the selected image, calls the predict image function to get the predicted class and confidence, updates the result label text in the GUI to show results. GUI setup. Root equal to tk creates the main application window. Root.title sets the window title. Root.geometry 400 into 500 sets fixed size of the window, adds a heading table label at the top, adds an empty label image label to later display the uploaded image, adds a browse button that triggers browse image when clicked, adds a result label to display prediction and confidence. Root.main loop keeps the GUI running and responsive. Main event loop. In the final output, the user runs the script, GUI window opens, user clicks select X-ray image, chooses an image, model predict class, COVID-19, normal, viral pneumonia, image opaque, image and prediction appears in the same window with confidence percentage.